So, Gwangmu from CSCS. Thank you.
So good morning, everyone. So like you heard before, this is not the keynote, by the way. Yeah. But anyway, good morning. So I'm Gwangmu. I'm a software engineer at CSCS. And today I'm going to talk about the next generation container solution, Sarus suite, and how we are using Podman, which is the, sorry, give me a second. So, which is the popular general purpose container engine, and we are using Podman at the heart of Sarus suite. And in this talk, I want to talk why we are using the general purpose engine for the HPC system and how we are doing right now. So in this slide, I think I was briefly thinking about introducing our center, but I think at this point you have heard about our center hundreds of times, so we don't need to go down into the detail. But instead, I just want to briefly remind you of the kind of the program that we are running on top of our system. So those programs are large. Those programs largely require some high performance, like you expected. So those are large-scale simulation and scientific modeling and machine learning model training, like expected before. So collectively speaking, we just call them workloads. Yeah, and being a program itself, we need some layers of software that sustain the software above the layer. Like there's a workload, and there are some dependencies that are required by the workload, and there are another dependency that are required by the dependency, and so on. So those are the software stack. So talking about the software stack, HPC software stacks are actually very simple, so very limited and simple. So the best solution was just installing them all. So that's actually what we did before until now. Yeah, and actually it worked. So our basic strategy was just installing them all and just let users to decide which software stack they want to use. But nowadays, just compare the scenario to the traditional HPC. So nowadays, mostly because of the ML AI, the kind of software stack that we need to support is actually very changing very fast. So it's not a solution to install them all before somebody is using them. Like if we try that, we install them one day, and the next day, and we wake up and we'll get some ticket from the user that says, hey, you can just install this software stack. So it's not the solution. So we just wonder, what is the solution in this situation? So for that, there's a conceptually very good solution called containers. So container is like a small package of the software. So you put software inside, like workload and the dependency, and you make a package. And conceptually, you bring this package to the system that you want to use. Yeah, then theoretically it should work. Yeah, this is great for a custom software stack. So, and that's why many HPC companies and HPC centers wanted to develop their own container engines. So, in this context, container engines are responsible for creating the container instance at runtime. So container instance is the container, in short. So nroot, like for example, developed by NVIDIA. But the caveat here is that those HPC container engines are more usually developed from the ground up. Yeah. So what does it mean? it basically means that it's fairly detached from the mainstream general purpose in short GP container engines here. They are evolving, their features are growing, and their communities is also growing. So they are not just heading toward the cloud-native computing, but they are tightly integrated into the cloud-native computing. So, and the general purpose engines are getting most of the benefits from these cloud-native computing paradigm. So what are the benefits of the cloud-native computing? So I'll just briefly tell you that cloud-native computing slightly reminds of the 1980s mainframe computing because of use of your laptop terminal and the backend of the cloud. But it comes with a lot of benefits, more than the mainframe computing. So the first and the important benefit that we are getting in our cloud-native computing is the development productivity solutions there. So imagine that you're developing something on your laptop using VS Code, but by developing something on your laptop, by default, the computation power is limited to the laptop. But with the cloud-native computing, so the backend of this computing will be on the cloud. So even if you are developing something on your laptop, the computation performance will be from the cloud. Yeah. So this is the benefit that we can get. Another benefit is that if we are using one cloud-native computing component, chances are using another cloud-native computing component can be a little bit smooth. So, for example, if we are creating a container image using Podman, then using the same container image for like Kubernetes can be easier. It's like that direct. And the last but not the least, the final benefit is the continuation of the benefits in the that I said before. So the ecosystem is very wide. So if you are having some problem, basically you can search for your problem on the internet and apply the solution to your system. And chances are they can work, most of them. Yeah. So those are the benefits. So if we are supporting containers on the HL system, it's very likely that many users will ask for some benefits of the cloud-native computing. Yeah. But we have no choice if we are using our own HPC engine. Yeah. So in this situation, so what is the best solution that to get through with all of that? So the naive solution is just using one of the general purpose engine on our HPC system. So to spill the beans, the answer is no, you can't. But let's pretend that we can just use it. Yeah. Then the best candidate can be Podman, because it's very modular and configurable, which is the great strength. Yeah, because if we want to use them on the HPC system, we may want to tweak something to make it compatible to the HPC system. So this is a good benefit. And if it's configured well, then it doesn't even require any privilege. So you can put users or workload inside a container. Then unless this workload or users want to break out of the container, it doesn't have any privilege. So it can compromise any system. So there are some benefits here. But just remember that we are using the HPC container engine, the HPC specialized container engine, and this is the benefit of the general purpose engine. So, so we may wonder why HP centers develop their own container engines instead of using the general purpose engine. And there are some good reasons here. Yeah. So even though general purpose engines are going to bring some benefits of the cloud-native computing, they are not compatible to the HPC system. So this, most of them result in the compatibility problem. Then you simply cannot run anything, or they just create some performance problem that significantly compromise performance. So let me briefly just go through the problems one by one. So the major problem is that the usage of the workload measure. Every HPC users know the standard flow of the HPC usage. So basically, you need to submit a job to the workload manager, that's Learn, and this workload manager will schedule this workload on the compute node, and the compute node execute the workload and just forward the job execution result. But as you can see, there's no container in this picture. So making the workload manager be aware of the container also the user is one problem that we need to solve here. So yet another problem is the usage of the shared storage. So shared storage is like a knot that ties the compute nodes together. Yeah. So theoretically, the intention is that the compute nodes can just query the central shared storage and get the same file from the same storage. Yeah. But the issue here is that the general purpose container engine like Podman just kind of implicitly assume that the storage device is attached to the computation that we are working on. So it makes a lot of compatibility issues here. So we also need to solve them. And the final major problem is that even after solving all these compatibility and conceptual problems, we still need to enable the HPC performance inside the container. So this performance is largely possible because HPC systems feature their own HPC hardware or libraries. But being inside the container means by default, it cannot see any HPC resource inside the container. So we also need to solve this problem to enable the full performance inside the container. So compiling all of that, so we propose Sarus suite, our next generation container engine. So putting Podman at the heart of our container engine is kind of a premise that we need to put there to get all the cloud native benefits here. But we also want to make it compatible to the HP system. So for that, we are just adding components around the Podman, and just remember that we are now modifying the Podman, because that way this is actually this is a high way to get detached from the mainline Podman and the Podman that you were using. So the main point of using Podman is getting the getting the cloud native computing benefit automatically, and Podman is updated. Yeah. So using the vanilla Podman is actually important in our for our purpose. If everything works, then we can just plug in the Sarus suite on our HPC system, and we can enjoy the container engine. So I will just briefly talk about how we enable Podman for our HPC system. So those are mostly meant to be addressing the problems that I mentioned before. So there were two problems here. So the first problem is that the workload manager is not aware of the container. And also the HPC users also don't know about the container, or they don't have an intention to use the container in the first place. So for that, we just add two components. We add two components for Sarus. So the first component is EDF. It's called Environment Definition File. So in this file, users need to specify which container image they want to use, or which directory they want to see inside the container. So the concept is that they are provisioning the environment that they want to use inside the container. So, and after compiling this EDF, they are supposed to submit this EDF file to the workload manager along with the job, the main job. And this is when the additional services component comes in. It's called Skybox. And this is the workload manager plugin. And this is responsible for comprehending the EDF file and provisioning the container environment in accordance with the EDF file. Then Sky also will put the workload inside the container and execute the workload inside the container and forward this job session to the users. And the second problem was the usage of the shared storage. Yeah. So for that, we introduced a utility called Parallax, and actually it does a lot of things, like to solve the compatibility issue between the shared storage and our and Podman. But I'll just talk about this one thing for the sake of the time. So one major problem is that usually Podman uses multi-layered content images. So this results in multiple transactions between the shared storage and the compute nodes. And this is very bad for the performance. So to avoid this situation, one of the jobs Parallax is doing is just squashing or flattening this multi-layered image into just one layer or layerless, so that a file transaction can be just one round trip instead of multiple round trip. The final problem was how to enable the HPC performance inside the container. So for that, we add the component called the performance extension for Sarus suite, and it does a lot of things too. Yeah, but I just want to highlight this one thing. So one of the things that it does is just injecting the hardware or libraries inside the container, so the workload inside the container can see the HPC resources or libraries outside the container. So this is very crucial if the workload inside the container want to take advantage of those resources to enjoy the full HPC performance. So I just show you this whole picture, And this is the red boxes are the Sarus suite components. And as you can see, Podman is at the center. And I just remind you one more time that we are not modifying Podman. We are using vanilla Podman. So the idea is good, but what about the practicality? Does it work, or is it just a plan? So we demonstrate that it's the working solution. We prepare some evaluation for with Sarus suite, and before we go into that further, I just want to remind you of the value of the Sarus suite one more time. So Sarus suite is the HPC container solution. So by being HPC solution, it should exhibit the performance of the HPC system. But we are not going to develop our own container engine. We are going to use the mainstream existing container engine so that using that engine can automatically bring us the benefit of the cloud-native computing. So if we agree that this is the value of the Sarus suite, there are largely three things that we need to check in this evaluation. So the first thing is whether Sarus suite can be usable for the existing HPC workload. So even if the concept is okay, if it cannot run any existing workload inside container, it's of no use. Yeah. So we need to show whether Sarus suite is capable of running the HPC workload. So and another thing is whether it exhibits the full HPC performance inside the container. So just merely running this HPC workload inside the container is not going to cut it. Yeah. So we want to show the full performance inside the container. And the final point is whether the usage of Sarus suite fits into the existing HPC usages, like submitting a job and getting the job result from the compute nodes. Yeah. So we'll see them, and when it comes to the usage, I just want to remind you that every single evaluation was done with the production CSCS supercomputers. So there's no node level tweaking or some developmental hack here. So this is the first evaluation plot, and as you can see, I just say this one thing first. So Node is the representative HPC content engine, which is written from scratch by NVIDIA. And Sarus suite is using the vanilla Podman from the upstream. And as you can see, the performance number, the truth number is actually the same between the two solutions here. And you can just compare the performance difference between the vanilla Podman and other HPC container solutions here, and Sarus. And you can see the huge difference between the performance. And this is another benchmark that we ran. This is first reconstruction, the modeling benchmark. And you can see the same trend in this plot. The Sarus suite and the HPC container solution is exhibiting the same performance, while the vanilla Podman is just staggering. And this is the final benchmark that we ran. It's called Dynamic, and this is the HPC benchmark for the storage system. And you can see the same trend here again. But one interesting detail is you can see the column with the number 32 here, where Sarus suite is performing slightly better than Alert. And this is because Sarus suite and Podman is written in the compiled language Go. But Alert is just a collection of bash script, which result in the slowdown in the execution of the container engine itself. Okay, so I'm going to conclude this talk with this one summary. So the container HP centers and HPC companies, they wanted to develop their own container engines because the general purpose engines have some compatibility issue with this engine and the HPC system. So they needed to develop their own container engine. But by developing their own container solution, all the benefits from the cloud-native computing is basically gone because it's the ground-up developed one. So instead of that, the approach of Sarus suite is just using the mainstream container engine, to get the benefit of the cloud-native computing. But we still want to enable the HPC performance inside the container. So for that, we added some components here, like workload measure integration or shared storage support, and we also enabled the HPC performance here. So the Sarus suite project is is going toward the completion. So we hope that we can integrate the Sarus suite in the real system in the coming few months. And I'll conclude this talk, and I will gradually get some questions from the audience. Thank you.
Thank you, Gwangmu.
Thanks a lot for your talk, and thanks for this project, which is really much needed in the community of users of HPC systems. My questions regards how well does this work in stuff that is not Python? Because all the benchmarks you showed were Python-based, which, if you want, it's a problem that was already solved in a hacky way by just writing your virtual environment in a shared file system of the cluster, and then sourcing it in your Slurm job. Instead, where this project will really shine is in those projects that are, let's say, more legacy, where you really need to compile your code, maybe a Fortran code from the 80s, against the optimized and maybe proprietary libraries that many clusters support. So let's say I have the proprietary InfiniBand drivers, and then I have an Intel compiler, and so on and so forth. And that would be great if it were possible to really package it in a container. So is Sarus able to do it now, or is there a future version that is going to tackle this issue?
So thank you for the great question here. So I'm just going to talk about my own take on that front. So when it comes to existing workloads, there are some solutions like installing the programs on the system directly, or using another solution that exists inside our center. So we just don't. I think maybe we can just continue using their solution because it's already working. So I'm not sure about the needs to port those existing workloads to this newer version. That's one thing. And another thing is that you briefly talked about the proprietary software here. So that is actually the challenge that we need to support inside the container. But the one thing is that we don't need to support every software inside the container, like infinite band. So we don't even have infinite band in our center. So that's just aside. That's another problem. And another problem is that another point is that we can support some of the proprietary software if we really need to support them. First, we can contact the companies that we want to run this software on our system. Can you work with them? Or we can use this kind of approach. Yeah. Yeah.
Do we have any other questions? Okay, thank you.